You ever wonder, where did all this come from? It's pretty much the biggest question we can ask. And for decades, we've had a standard story for how our universe began. But what if that story has a challenger? A rival idea that suggests our universe might not have had a beginning at all, or an end. So here's the central puzzle that any theory about our origins has to solve. Why does our universe look the way it does? When you zoom all the way out, it's incredibly uniform. It's also geometrically flat. So any good story has to explain, how in the world did it get smoothed out so perfectly? For the longest time, one theory was king when it came to explaining the smoothness. But now, an older idea is making a comeback, and it's supercharged with some pretty compelling new evidence. It's challenging everything we thought we knew about the Big Bang itself. All right, so first, let's talk about the reigning champion, the theory of cosmic inflation. This is the story of our universe's birth that, you'll find in pretty much every textbook today. The idea is actually pretty straightforward. It says the universe burst into existence from a single, infinitely dense point, what we call a singularity, the Big Bang. But then, in a tiny fraction of a second, it went through this period of absolutely mind-bogglingly fast expansion. This inflation was like blowing up a balloon, stretching out any wrinkles or curves until everything was almost perfectly flat and smooth. And here's the thing. This theory really works. It brilliantly explains the universe we see around us, from its flat shape to how all the galaxies are spread out. And that's exactly why it's been the leading idea for decades. But this is where the story gets a twist. One of the original architects of inflation theory, a physicist named Paul Steinhardt, has now become one of its biggest critics. So why would a creator turn against their own creation? Well, it turns out inflation comes with some pretty strange baggage. The theory suggests that this rapid expansion wouldn't just stop everywhere at once. Instead, it would keep going forever, constantly spawning an infinite number of these little pocket universes. We'd just be one tiny bubble in this endless bubbling cosmic foam. And this quote from Steinhardt gets right to the heart of the problem. If your theory can create an infinite number of different universes, then it can't make any specific, testable predictions about our universe, right? It kind of explains everything, which means it ultimately explains nothing at all. And this philosophical hang-up is what pushed him to search for a better idea. So let's meet the challenger. This is a totally different way of thinking that gets rid of the single beginning and the multiverse. This is the story of the universe on a loop. Just look at this concept. Instead of one single bang, imagine an eternal cycle. Our universe expands, then it slowly contracts, it bounces, and then it starts expanding all over again, forever. There's no single starting point, just this endless cosmic breath, in and out. The formal name for this is the cyclic or sometimes ekpyrotic model, and the key event here isn't a bang, but a bounce. The universe doesn't shrink down to an infinitely dense point. Instead, it contracts down to a very small size, recharges its energy, and then rebounds to kick off a new cycle of expansion. Okay, so how does this idea solve that smoothness problem we talked about? This is my favorite analogy from the source material. Inflation smooths things out by blowing everything up really fast, like stretching the surface of a balloon. The bounce model, though, does it during a long, slow period of contraction. It's like you're looking at the universe through an increasingly powerful magnifying glass. As your view shrinks, everything in it just naturally appears flatter and smoother. So here's how the cycle is thought to work. The universe expands for maybe 1 trillion years. Then it starts a very, very slow contraction that lasts for billions of years. And that slow squeeze, that's the secret sauce. That's what irons out all the wrinkles. This contraction also recharges the cosmos with energy, which leads to the bounce that kicks off the whole thing all over again. Okay, so now we have our two main contenders. One is a story of a single explosive birth. The other is a story of an eternal cyclical life. So let's put them side by side and see how they stack up. And this image just illustrates the difference perfectly. Up top, you've got inflation, a single starting point, that crazy fast burst of expansion, and then our timeline unfolding. But below, you have the cyclic model, a contracting phase that does all the smoothing, followed by a bounce, and then our current expansion. It's a totally different history of everything. This table really just breaks it all down. Inflation theory, it needs a single Big Bang. It uses rapid expansion to get smooth. It requires that weird singularity at the start, and it leads to an infinite multiverse. The cyclic theory, no beginning, no end. It uses a slow contraction for smoothing, it avoids the singularity with a bounce, and it results in just one single repeating universe. So where does this cosmic rivalry stand today? Well, for a long time, the bounce was kind of a fringe idea. Not really in the mainstream. But that's starting to change.
What's really cool is that recently physicists have been using these super powerful computer simulations to see if the bounce model actually holds up. They're throwing everything they can in it, starting the simulation with these incredibly lumpy, chaotic, just wild universes to see if that slow contraction can really iron them all out.
And the results have been, well, kind of stunning. According to Steinhardt, it didn't matter how messed up the starting conditions were. You let the simulation run, and bam, that slow contraction phase just erases all the chaos, and you end up with a smooth universe that looks just like ours. This is a huge win for the theory. Now, let's be clear, inflation is still the dominant theory. It's the paradigm to beat. But with this new evidence from simulations, the cyclic model is being taken way more seriously than ever before. It's graduated from just being a cool idea on a chalkboard to a real viable contender. And all of this leaves us with this one profound question to chew on. Are we living in a cosmic accident, a one-time fluke in an infinite sea of other universes? Or is our entire cosmos just the latest version, the latest chapter, in an epic and eternal story of collapse and rebirth? The debate is far from over, but the questions it's asking, they get right to the heart of who and what we are.